Hi, everyone. Welcome to GIA Knowledge Sessions. These are a series of talks and seminars about gemology that are fueled by our decades of research at GIA. Here, we really consider ourselves to be very fortunate to get to study and learn from gems, and it's our mission to share our discoveries and our findings with you. And so I'm excited to kick things off today. My name is Dr. Mike Breeding. I'm a senior research scientist at GIA. And I'm joined by Dr. Yun Lua, Director of Metrology and Quality Control at GIA. Today, she's going to tell us all about quantifying fluorescence and the impact fluorescence can have on the visual appearance of diamonds. So before we get started, a little bit of housekeeping information. Everyone attending the webinar is automatically muted. If you have a question, please submit it using the question and answer feature you'll see at the bottom of your screen. Please do feel free to ask questions though as we go, and I'll compile them and we'll ask Dr. Lua at the end to give us some enlightenment on some of your questions and ideas. So during that Q&A session, she'll go through each one and hopefully we'll give you all the information that you need. We'll also be sending a recording of the session to you later today. And that message will also have a survey. So please fill that out. We'd love to hear your feedback. It really helps everything go smoothly and better for us. So with that, I'm going to pass you to Dr. Lua, and she's going to take over. Hey, Yun.
Thank you, Mike. Thank you, everyone, for joining us in this GIA knowledge session. Today, we're talking about the effects of blue fluorescence on diamond appearance. This is actually not new. This topic has been generated very vivid discussions and even very hot debates in our industry for quite a while. So in today's discussion, we will review some history of the blue fluorescence in diamond, together with the new technologies we're able to use nowadays to quantify diamond color and fluorescence and its impact on diamond appearances. I hope this can provide more insights to the trade and make people to look at diamond fluorescence in a little bit differently. Let's start off by a very quick review of fluorescence in diamond. Fluorescence is the emission of light by a diamond when it absorbs UV radiation. So when an electron absorbs the UV radiation, it moves from its ground state, which is also called a stable state, into a temporary high energy excited states. This high energy state is now stable, so the electron relaxes back into a lower energy state that is slightly more stable. As the electron falls back into its ground stable state, the diamond emits light. And this emitted energy is always less than the excitation energy and is called diamond fluorescence. The microscopic structure that allow this movement of electron are called luminescence centers. They arise from different defects in the crystal lattice in diamond. The most common blue fluorescence in diamond are produced by the N3 center, which is shown here. And it consists of 3 nitrogen atoms surrounding by a vacancy. We also have other structure defects produce other colors of fluorescence under long wave UV, such as the yellow-green fluorescence from H3 and H4 center, and the orange fluorescence from the 480 band, and the red fluorescence from the NV center. You can almost make a rainbow out of here. In this study, we focused on the blue fluorescence since it is the most common one from diamond. Sally actually shared many stories on the famous Hope diamond in the last GIA knowledge session. I want to borrow one story from her, which is from the 1600s when Jean-Baptiste Tavernier bought the French blue, which the Hope diamond was cut from. Tavernier is the first European to describe the diamond mines in India in his books, The 6 Voyages. He also documented some very interesting facts about diamonds and how people evaluated them back then. And I found this paragraph particularly interesting, so let's read it together. As for the water of the stones, it is remarkable that whereas in Europe, we make use of daylight to examine the rough stones to judge of their water and specks that are found therein. The Indians all do all that in the nighttime, setting up a lamp with a large wick in a hole which they make in the wall about a foot square, by the light whereof they judge of the water and the cleanness of the stone, which they hold between their fingers. The water which they call celestial is the worst of all, and it is impossible to discern so long as the stone is rough. The most fillable way to find out that water is to carry the stone under a tree thick of boughs, for by the verdure of that shade, you may easily discern whether the water be bluish or not. So trying to connect what Tavernier is described here with our modern terms, I think they were evaluating the diamond clarity, which is the cleanness of the stone in this paragraph, the fluorescence of diamond, which is the bluish water. They might also say the cloudiness or the haziness of the diamond, which they describe as the worst celestial water. It's very fascinating to read that people were observing diamond appearances under different lighting conditions, even over 300 years ago. And those appearance characteristics are not too far away from what we are doing, what we are evaluating today. There are many events and the stories associated with diamond fluorescence. Along the line, there was totally turnover of the perception of fluorescence in diamond, from a not questioned positive characteristic to a very negative perception. Historically, the trade has given names to certain types of fluorescent diamonds based on the mines that produced significant amount of such stones. For example, the term premier has been used to describe light yellow diamonds with strong blue fluorescence, because such diamonds were often found in South Africa's premier mine. The term jagger has been used to describe colorless stones with strong fluorescence. The name is originated from the Jagersfontein mine in South Africa as well, where such diamonds were commonly found. In these early days, the fluorescence in diamond was not questioned, and some diamond dealers would seek out near colorless to light yellow diamonds with strong blue fluorescence because they believed that the blue fluorescence could neutralize the yellow component in the diamond and give rise to a diamond that appeared more colorless under a lighting condition with high UV content. These diamonds were marketed as the blue-white at that time. It was in 1938, this blue-white term was prohibited by the US Federal Trade Commission. I think it was right to bring transparency and accurate terms and information into our industry, but I see this comment of misuse of the term blue-white associated with the fluorescence as a seed for the growth of the negative perception of fluorescence in diamond. Especially later in the trade, people also observed that some gem diamonds with a hazy appearance also fluoresced strong blue under UV radiation. And then in the dynamic market of the late 1970s, there were diamond dealers who started to avoid diamond with fluorescence when they traded diamond remotely, since they worried that those diamonds were over blue, and then the dealers at that time began to offer substantially lower prices for what they call the Milky Ds, which they refer to as a diamond with a color grade D, very strong blue fluorescence, and also with a haziness appearance with the diamond. It was not until 1993 the reputation of the fluorescence in diamonds was really tarnished during this Korean blue crisis. It was a TV show in South Korea reported that fluorescent diamonds are worth much less than non-fluorescent diamonds. So reading into this story reported by Rapport, we learned there was a really strange practice by Korean grading labs at that time to undergrade their diamonds. So a GIA graded G color internal flawless diamond would become a H color VVS1 in Korea. They do this to protect their local customer and dealers and to limit competition from the international market. The only one area in which the Korean labs had been more lenient than other labs is that they generally upgrade color for fluorescent diamonds. For example, they often grade a normal G as a H color, but a G with strong fluorescence had a good chance of getting an F color grade in Korea. As a result of such biased grading, Korea attracted a very high percentage of fluorescent stones at that time. Survey indicated that there are over as high as 70% of fluorescence diamond in Korea market at that time. Then we had this TV attack focused on only the fluorescence aspect of diamond, and reported diamond with fluorescence was worth up to 60% less than diamond with fluorescence. It was unfortunate that the TV program did not make it sufficiently clear that the fluorescent diamond were worth less due to the misgrading by the Korean labs at that time, not because of anything negative that fluorescence had impacted on the diamond itself. However, the impact of this crisis lasts since then. So along this time, GIA and its peer laboratories continue researching in diamond color fluorescence, as well as the effect of blue fluorescence on diamond appearances. Back in 1981, Shipley and Liddycoat from GIA emphasized the importance of controlled lighting condition for grading, including diamond color and fluorescence. And in the 1970s, GIA's grading report included a comment for diamond with medium to strong blue fluorescence, which reads right here: the ultraviolet fluorescence of this diamond enhances its color appearance in daylight. And in the 1997 research by GIA, the effect of blue fluorescence on the appearance of diamonds was studied by visual observations under controlled lighting environments. This study found that strongly blue fluorescent diamonds were perceived to have a better color appearance when viewed face up, and there was no noticeable trend face down. Most observers saw no relationship between fluorescence and transparency. In a more recent study by HRD, they concluded that the simulated outdoor lighting improved the grade of diamond with strong and very strong fluorescence when viewed table down, and the table up effect was less pronounced. Despite there was no negative effect of blue fluorescence on diamond appearance were reported from all these studies, blue fluorescence still negatively impacts the diamond prices till now. So in the same 1993 issue of the REP report, we can see this price indication for blue fluorescent diamond. We can see that there were penalties and discounts on the fluorescent stone in the D2H ranges here. And there was a slight premium on the fluorescence in the lower color I2N range. And 2 decades later, this chart we downloaded from REP report, it's from 2020. And the discount, actually the premium on the low color stone disappeared, replaced by penalty discount here. And the discount increased across all colors and fluorescent intensity along those ranges. Fluorescence as a characteristic property of diamond cannot change, right? So this belief that blue fluorescence of any intensity negatively affects diamond appearance, thus its price, is getting stronger and stronger in our industry. What does this mean to us as consumers? Let's do a quick shopping. See, today when we want to buy a 1 carat round brilliant diamond, I think F color, VS1, clarity are reasonable. Let's also choose the XXX, so we have excellent cut, symmetry, and polish on the stone. Here from Blue Nile are 2 stones that meet our criteria. With everything else the same, one has no fluorescence and one has strong fluorescence. We can see the price difference between those two is almost 3 grand. What is so bad in this strong fluorescent stone, or what is so much better in this non-fluorescent stone here, which can justify this 3 grand difference in price? This brings us to the goals of our study and today's discussion. We want to provide a better understanding of the effect of blue fluorescence on diamond appearance and quantify it instrumentally. We hope that this will help to reduce the confusion and the biases in the industry and serve as a solid scientific foundation to ensure public trust with respect to diamond fluorescence. So when light strikes a diamond, a small fraction of the light is reflected while the rest is transmitted through the stone. As the light passes through, it may be refracted, absorbed, or scattered by atomic scale defects in the diamond structure or inclusions, and it can be internally reflected by special arranged facets in a well-cut diamond as well. Ultimately, the resulted wavelength of lights that exit the stone and return to the observer create the color and appearance of the diamond. Whenever we talk about the appearance of diamonds, there are three major factors that always need to be considered in order to make valid evaluations. So the object, the diamond itself, the lighting environment, and the viewer, which can be a camera or our human eyes. Here on this slide, we're seeing the pictures of the Portuguese diamond taken under different lighting conditions. This first one on the upper left emphasizes its clarity, which is VS1. And this one to the right shows its color, which was graded M color by GIA. The Portuguese diamond has a very strong blue fluorescence and has been cited as a classic example of overblue and exhibiting a noticeable hazy appearance, which is shown in this picture. It is obvious that lighting plays a very important role in evaluating diamond appearances. Historically, there are three major challenges we need to overcome in order to better understand the effect of blue fluorescence on diamond appearance. The lack of a standard illumination, the fact that color and fluorescence both correspond to a range of values, and the lack of a standard methodology to quantify color and fluorescence. I want to spend some time in the next couple of slides to discuss those some major components of these challenges to see if we can understand them better and overcome them. Start with the most important factor, the illumination. If we are like the Europeans and the Indians in the Tavernier story, one always use daylight and one always use the lamp candlelight to evaluate the appearance. We will never agree with each other. And the GIA team recognized the importance of controlled illumination since the 1940s and always believes that a standard light source used to evaluate diamond color and other appearance characteristics should always have K daylight elements, including a UV component. So in this chart, we compare the UV content from different light sources. Daylight from a sunny day has the most UV, followed by daylight in a cloudy day. And the light yellow spectrum here is from a GIA diamond dog. It has a similar UV content as the cloudy day. And the office lighting, which is the light blue spectra down here, it has the least UV content. And some of us in the diamond trade argue that because typical office lighting lacks the 365 and the 385 long wave UV, it reveals the true color of diamonds. So what is the true color of diamonds here? Is it the color of diamond viewed without the long wave UV radiation? So the color is not affected by the blue fluorescence from the N3 center. In the next two slides, I want to show this might not be the best way to define the true color of diamonds. Let's first take a look at this blue spectrum here. When we use the 365 nanometer UV to excite N3 center in diamond, it will emit the fluorescence as shown by this emission spectra here. It has characteristic 3 peaks at 420, 429, 439, and 450, sitting on this broad band between 400 to about 500 nanometers. And this gives the fluorescence blue color. And this 3D fluorescence spectra here shows the N3 emission at a different excitation wavelength. If we take a cross section at 440 emission, as shown in the red here, we can tell that the blue fluorescence caused by the N3 center defects in diamond can be activated by wavelengths from about 350, which is right here, to all the way up to about 420 nanometers. This means all the wavelengths here in office lighting will activate N3 defects at different efficiencies. So a diamond color will be viewed with some amount of blue fluorescence, even under office lighting. Here we have a good visual demonstration. So this overhead lamp from a testing microscope has no emission below 390. So we don't have any 365 or 385 long wave UV peaks here. The picture on the right shows two G-color diamonds with similar size imaged together under this overhead lamp. The stone with strong fluorescence on the left glows blue in this light without long wave UV peaks, while the non-fluorescent diamond on the right does not. This illustrates again the importance of using a standardized illumination with fixed UV content to define the color and study other appearance factors of a diamond. The second challenge here is the fact that both color and fluorescence evaluations correspond to a range of values. These two stones, A and B, both have eye color, but the B stone has more yellow component in it than A and is close to a lower J color. If they both have strong fluorescence, remember fluorescence grade here also has a range, but B stone has less blue intensity compared to A. So even under the same lighting condition, the effect of strong blue fluorescence will be different on the eye color from these two stones. The stone A with stronger fluorescence here will show a better color compared to stone B. This makes consistent and accurate visual comparison very challenging. The third challenge is the lack of a standard methodology to quantify color and fluorescence. In this study, we use imaging systems to measure what we see, to demonstrate and quantify the effect of blue fluorescence on diamond appearance. So a quick color 101 here. This chart is an illustration of the LCH space. LCH stands for lightness, chroma, and hue. Lightness, also known as tone, refers to how dark light the color is on a grayscale from black all the way to white here. And chroma refers to a color's intensity or saturation. Hue here literally means the color red, yellow, green, or blue. To measure the table down color, the diamond is sit in the center of a sample chamber here in a very controlled lighting environment. And the pictures were taken by camera at a specific angle. The image of the diamond were processed and the LCH information was extracted to evaluate the diamond color. Imagine where we slice off a yellow pizza from this rainbow pizza in the horizontal plane and move it right here. We have a series of diamonds arranged in this section. Both hue and the lightness are very narrow, in a very narrow constrained range, which means this set of stone have the same yellow hue and the lightness are similar as well. But we can see from up top to the bottom, the chroma values of those stone increases as the yellow component in the stone increases. So basically the higher the chroma, the more yellow in the stone, which indicate a lower color grade for this diamond. The measurement setup for fluorescence color and intensity is similar. We have the UV source on the top here. Diamond is in the center of the sample chamber, right below the UV source. And the camera are sitting at this direction to take images. Again, the images are taken and then are processed to extract the LCH information to evaluate the fluorescence color and intensity. So different from color measurement here, no pizza anymore. We're actually looking at a very thin cylinder here in this very constrained blue hue, which is parallel to this lightness axis from dark to light. So if we move this cylinder to the set of samples here, they are all constrained with the same blue hue and with similar chroma. However, it's the lightness of those measurement changes from very small to large, and a very small lightness means dark. So the fluorescence is either weak or there's no fluorescence. And as the lightness value increases, we see more intense of the fluorescence. The blue color becomes more vibrant, and the fluorescence is getting as a strong fluorescence grade down here. So in this study, we measured the effect of blue fluorescence on diamond color as it's evaluated using the GIA traditional table down position, the diamond color in the more straightforward face up position, and the brightness of the diamond, which is the total light reflected from the diamond in the face up view. Last but not least, we are also trying to measure the transparency of the diamond. So for the table down color, we measured many sets of stones with the same color grade and similar proportions on our color measurement device with incremented UV steps. As all of the color sets we tested showed the same trends, this chart here shows the result we obtained from an F color set as an example. So here the y-axis displays the chroma measured on each stone, and the x-axis corresponds to the stones with different fluorescence intensity. So just take this non-fluorescence as an example. The four dots here corresponding the measurement on this same non-fluorescent stone with incremented UV steps. So as we can see here, as we increase the UV intensity here, the non-faint and the medium stones don't show obvious color change, whereas we can see for the strong and the very strong blue fluorescence diamonds, there is a very sharp decrease in chroma in those samples. And in the next couple of slides, we use this non and very strong fluorescent stone to make visual comparisons of color and brightness. So viewing table down from left to right here, this non-fluorescent stone does not show obvious color change when we add UV component into the environment. By contrast, this very strong blue fluorescence F color stone displayed a whiter body color under the UV containing environment. The same trends were observed for the face-up color and brightness. So for this non-fluorescent stone, the color and the brightness do not change with and without UV, while this very strong F color stone, again, it showed better face-up color and brightness with UV. As for the brightness, it makes sense if we consider the mechanism of fluorescence converts invisible UV light into visible light, thereby increasing the observed total light return. So we have improved brightness here together with the face-up color. As we mentioned earlier, different light sources that are used to inspect or grade diamond contain different distribution of UV light intensity as a function of wavelength. Each of these wavelengths will interact with N3 defect with different efficiency. From this chart on the left, we can tell a diamond with only N3 defect excited by a pure 350 light to be approximately 1/3 as bright as the same stone excited by the pure 370 light here. We can calculate the total area under the normalized N3 excitation curve as the indication of N3 excitation efficiency from different light sources. From this table, we can see that expected fluorescence brightness is not 0 for the office light and even for our colorimeter measurement system with no UV. Again, it is important to note that even a system labeled as only white light or office light with no UV, it still contributes to the blue fluorescence. Again, we cannot stress enough that standardized illumination with fixed UV is essential. This provides the baseline for the consistent evaluation of diamond color and overall visual appearance. Let's use GIA Diamond Dock as our baseline here. If a set of stones with similar color but different fluorescence intensities, if they are brought to a higher UV environment, such as outside under daylight, we would not expect to see any observable changes in color and brightness from non-faint and medium fluorescent stones. In contrast, we would see enhancement in color and brightness in strong and very strong fluorescent stones. And if this same set of stones were exposed to an environment with less UV, such as office lighting, again, non-faint and medium fluorescent stones will stay the same, while the strong and the very strong fluorescent stone will get slightly impacted. However, we need to always keep in mind, even under this office lighting, it's still excites blue fluorescence, and the color you observe down, under the office lighting will always have a blue fluorescence component in it. So let's switch gear to take a look at the milky white transparency issues, which I think is the major reason behind the negative view of fluorescence. These two stones are from our D color sample set with the same color grade and similar proportions. Under a microscope, some of us see that the non-fluorescent stone on the right looks very crispy clear, but the very strong fluorescent stone on the left appears softer or hazier. Is this really the haziness in these very strong D color stones? And how does it correlate to fluorescence? Let's take a look at fluorescence intensity versus the haziness here. We have seen many sets of stones with the same color grade, similar proportions, and with the same fluorescence intensity range from none all the way to the very strong. They all exhibit the same crispy, clear transparency. We have also observed stones with non-fluorescence and strong fluorescence that show the same level of slight haziness. We have seen diamond with medium and strong fluorescence that have very obvious haziness. And lastly, this faint fluorescent stone was so milky, hazy, and it qualifies as a fancy white diamond. From the outset, we could not find a reasonable correlation between fluorescence and the observed haziness. To give ourselves a viable direction for study, we proposed one possibility and asked two questions. We think the light scattering from diamond structure defects actually cause the perceived milkiness or haziness in diamond transparency. And our questions are, does fluorescence really cause haziness and reduce transparency? And what happens when fluorescence come together with the structure defects? Since we set up measurement systems to quantify color and fluorescence, we wonder if we can do the same thing, measure transparency as well. We were lucky to come across a technique called the modulation transfer function. It is also called MTF here. So in the optical world, MTF is routinely used to evaluate the performance of optical systems. Here, we use the MTF principle to measure the contrast reproduction of diamond plates. This is what it looks like in the real measurement system. Bar targets are imaged through diamond plates with different fluorescence intensities, with and without UV excitation. And the selected area are isolated for measurement analysis to calculate the contrast percentage values. To calculate contrast, we assign a maximum value to the white bar here and a 0 value to the black bar here. So as we go from left to right, the black gets less black, it turns to gray, and the white gets more gray into it. And we can see the lightness value for this white decreases and the lightness value for this black increases. This is contrast loss, and mathematically, contrast is calculated by taking the percentage of the difference between the lightness max and the lightness minimum divided by the sum of them. So our system is set up in a way that by seeing through a diamond plate, we were able to calculate the percentage contrast for different bar targets. This chart shows the contrast measurement made on a medium fluorescence diamond plate with and without UV excitation. So this blue line here is the data taken without UV radiation. And as it's excited by the UV, we can see there is a contrast loss on those bar targets. We have performed this MTF study on diamond plates with non, medium, and the strong fluorescence diamond. And we can see there is a linear relationship. The y-axis shows the contrast difference between measurement taken with and without UV. The x-axis here corresponds to the different fluorescence intensities. So when the diamond plates were exposed to UV, we don't see contrast loss from the diamond plates with no fluorescence, but we do observe contrast loss in the medium and the strong fluorescence diamond plate. Fluorescence, so we can see that fluorescence in diamond plate cause minor contrast loss when they expose to UV. So what does this contrast loss mean when we look at a polished diamond? Going back to the 2D color stones we saw earlier, from this non-fluorescent stone, we see a very distinct pattern, which means there are sharp edges between dark and bright areas. But if we look at the similar pattern when the stone is fluorescing strong blue, overall, we still see the fluorescence makes the stone brighter. However, in terms of contrast, if the black lessens and the white turns to blue due to the fluorescence, we will see contrast loss. But does this contrast loss mean haziness here? We don't think so. A testing microscope was mentioned earlier in this talk, and it is actually an excellent tool which can help us to distinguish between haziness due to light scattering and the so-called fluorescence effect. As you can see, there is a UV component in our current GIA microscope, both in the overhead lamp and the dark field illumination. However, the dark field illumination from this testing microscope here contains absolutely no UV or any wavelength below 420. Remember that N3 defect can be activated by wavelengths up to 420 nanometers. So if we put a strong fluorescent stone under this dark field illumination, we can be assured that anything we see is not caused by the fluorescence, the blue fluorescence from N3 center. Now we can choose meaningful sets of samples to compare between these two lighting environments. One contains UV and the one with no wavelengths that could excite the common blue fluorescence producing N3 center. So under our GIA microscope with UV, this non-fluorescent stone appears crystal clear, while the strong fluorescent stone looks very hazy. Without UV, the strong fluorescent stone still hazy. Again, remember, we were assured that anything we see here are not caused by the blue fluorescence from N3. Obviously, here, fluorescence is not the main contributor to the haziness here. Here we have two stones. One has very strong fluorescence, one has no fluorescence. Both are clear without UV. Viewed under UV, the very strong fluorescence glows beautifully, and visually it's very easy to see. Would you call this stone hazy? The last set shown here are two strong fluorescent stones. Without UV, one appears clear, while the other one is not. The other one shows very hazy here. And with UV, we observe the same thing. However, what appears to be the natural haziness of this stone together with the fluorescence makes the stone look wider, brighter, or more brightness return, however you want to call it. But does this mean this stone is hazier? Maybe. So the transparency part of our study can be summarized into 4 points. First, the milkiness or the haziness in diamond is mainly caused by light scattering due to structure defects. And our MTF study on diamond plates shows there is a minor contrast loss when the fluorescence sample is exposed to environment with UV. However, the contrast loss induced by fluorescence is not the negative haziness we see in some of the diamonds with or without fluorescence. It is likely that fluorescence in the stone together with the structure defects increase diamond's perceived haziness under an environment with UV. We realized that we are not really dealing with the see-through transparency here, right? We're looking at the face-up pattern when we say this stone is clear, this stone is hazy. Both fluorescence and light scattering from structure defects can cause contrast loss when we look at the stone face up. And it is extremely difficult to distinguish between them in many cases. So we started to experiment with this bulk contrast evaluation method. In this method, no considerations were made as to what caused the perceived haziness in the sample stones. It can be fluorescence, it can be graining, it can be clouds or anything. We only look at the contrast loss in the face-up pattern. In this chart, the x-axis is the brightness of each pixel in the image, with 0 all the way down here being absolute black, and 100 be absolute white. For this relatively clear stone, which are color-coded by blue here, we see a fair amount of distance between the black peak and the white peak. As the stone get hazier, as coded by red and green here, we see contrast loss. The pixels get less black and less white. They're moving from this direction and to this direction. We think this may serve as a reliable way to quantitatively evaluate the effect of contrast loss on apparent transparency in future diamond grading process. We're almost there. I wanted to talk a little bit about this art piece over blue featured on the cover of summer G&G issue this year, because I really like it. The proportion of the sketched diamond actually relates to the reported occurrence of different fluorescence intensities. Start with the most abundant non-fluorescence to be 68%, followed by about 21% faint fluorescence diamond. And 70% diamonds have medium fluorescence, 4% diamond has strong fluorescence, and only 0.24% diamonds show very strong fluorescence. The art acknowledged that the subtle effect of fluorescence on diamond appearance usually not noticeable for almost 96% of diamonds we see in the lab, which including non, faint, and medium fluorescence. And when the fluorescence reaches to strong and very strong, the light-dark contrast of the face-up pattern softens with a unique blue glow. So here is the takeaway message. We believe fluorescence is a unique intrinsic property of about 30% of diamonds. It can enhance color and bring about increased brightness when we go outside, even though it may cause minor contrast loss on the diamond face-up pattern when it glows blue. We see no evidence that fluorescence alone produces noticeable haziness or reduced transparency in diamonds. Plus, fluorescence looks very beautiful as shown in this cover from the 1997 G&G, and it can be super cool in certain cases, like this rainbow fluorescence we see in one diamond in the lab. So I'll stop here. Thank you everyone for your attention, and I can take any questions you may have.
Thank you very much, Yun. There was a lot of good information in there, and we do have some questions from the audience. So let me see, let's start with, you had talked about the controversy in the Korean market with the Korean blues. We have a question asking if you know what prompted the market to grade those fluorescent diamonds differently. Was it political or for some sort of value gain, or do you know much more about that?
Not really. From my study into that story, I think the whole thing is politically or local market driven. But the reason why they upgrade the fluorescent, the diamond color with fluorescence, I don't know. But I think that example showed we should not, like as a grading lab, it should not involved in a marketing, and that's very dangerous.
Yeah, it's a pretty crazy situation. So, and it led to a lot of wild changes around the world, huh? So let's see, we have another question. When you talk about LCH descriptions of fluorescence, maybe I'll simplify the question by simply saying, can you speak a little bit about the difference between what the terms lightness and chroma mean?
Yeah, so lightness, this is, it's not easy to understand or to grasp. So let's talk about blue fluorescence. so you can see with a strong blue fluorescence, the color is still blue, and you see more brighter and whiter component into that blue. And then compared to a faint fluorescence, you still see blue. That's the blue fluorescence. However, the lightness we see is darker or blacker. So if you remember that LCH space, we actually assign the black as a 0, the white as a 1, which is the maximum lightness you can have in there. So the more whiter, brighter component you have, the higher the fluorescence intensity. So I hope that makes sense.
All right, thank you. Yeah, I just think a little bit of clarification, I think that was good. So there's also a question when you talked about the different types of lighting and you were comparing them like daylight and office light. Someone was asking particularly about office light. Do you have a thought on whether your representation of office light is more of a fluorescent tube style or more modern LED style?
The office light we took in this study is the fluorescence light. And I think we spend a lot of effort to study different light sources. We also studied the LED office lighting as well. I think those spectrums provide a reference. It's like when we report color or when we report fluorescence, we want to, I think at this point, we want to disclose what kind of lighting environment we observed or we graded. But we asked for like so many times in the talk that we need a standardized light source. If we can reach upon a standardized source, I think everyone can be on the same line. We don't need to disclose or explain what our light looks like and what a diamond are graded or observed under what kind of light source.
All right, thanks. And then I'm getting flooded now with questions about laboratory grown diamonds. And I know, having talked to you, it's not something we've looked at into a ton in terms of this study, but people are asking about whether you see haziness in laboratory grown diamonds and also whether you see blue fluorescence in laboratory grown diamonds. So I have some input on that, but I'll see if you had anything you wanted to say, and then maybe I'll add a couple of things.
Yeah, so I'll just talk a little bit, and then Mike is an expert in that. So I think we need to go to the root cause of the fluorescence and haziness in diamonds, right? So if laboratory grown diamonds can contain N3 center or can contain those structure defects like those plastic deformation, the nano inclusions, or the internal graining, and then they will show fluorescence and will show haziness, right? So Mike, I'll pass it to you.
Yeah, I mean, in terms of haziness, the root understanding from the study is that a large bit of haziness in natural diamonds is caused by structural imperfections. And there are some of those in laboratory grown diamonds and CVD diamonds and things like that. So there's no reason why you can't have something similar. The fluorescence, however, tends to be pretty different in laboratory grown diamonds. You rarely get blue fluorescence. It does happen once in a blue moon, so to speak, but almost never really amongst the common lab grown diamonds that you see. If you do see it, the nice thing about it is the fluorescence in lab grown diamonds tends to be stronger to shortwave ultraviolet light than the long wave, and the opposite is true in natural diamonds. So you've always got that. Even if you do see a little bit of blue, it's probably not going to be the long wave UV for lab grown diamonds. So hopefully that answers. I know there were a lot of questions here. A bunch of them came right at the end. So let's see. Sort of a side question, Ian. Would you at GIA, when we grade color and we describe fluorescence in diamonds, do we do that? Do people do that, or do machines do that, or how do we do that?
Well, I can say we use both. We use device and we use visual as well. So I think in this modern world, we cannot say we only grading diamond by visual. I think the diamond color grading system and fluorescence grading system were established by visual. And along the way, when we trying to develop instrument to better accurately or consistently measure those characteristics, we try hard to make sure the standards carried along. However, as the same as any other measurement systems, like the way we measure color and the way we measure fluorescence will have their limitations. That's when we refer to visual. And I think visual and instrument always complement each other, and we use them both.
All right, thank you. And on your last slide, you have some crazy looking rainbow fluorescence. Can you speak any more about that and what causes that, or why it looks that way? And also, what sort of grade would GIA give on a diamond like that? Or not a grade, excuse me, a fluorescence description would they give for a stone like that?
I would give it a medium rainbow, but I think that stone is very special. I think so. I just answered the question what the fluorescence grade is on that stone. I think it was graded as a medium orange, and the reason being that orange is the predominant color in that rainbow. The reason why we have a rainbow there is that stone was actually a multiple treated diamonds. It has gone through a different treatment process. And again, remember the luminescence center, those defects in crystal lattice, we have different kinds of them. And that's how those different fluorescence color in that stone are coming from.
All right, maybe we'll wrap up with a couple of last sort of general questions, and these are kind of opinion questions, I think. But a couple of people have asked, given the new sort of insights on fluorescence and its effect on diamond, and older ones as well, should fluorescence be considered a key component to diamond shopping? I mean, is it as important as the 4 Cs? And also, kind of, where do you have any opinion as to where the industry may be going with regards to pricing on fluorescent diamonds?
Well, personally, I hope industry can take her 10 and do not penalize those strong fluorescent stone, which also looks beautiful, clear, showed in our slides. And for fluorescence, I think at this moment, I would say it's still a personal preferences, like, but for me, I really like fluorescence in diamonds. It's like an internal glow of diamonds. That's really cool.
Cool. Thank you, Yan. I think we'll wrap up the questions. Feel free, anyone who had questions that we didn't directly address, you can feel free to email someone at GIA and we'll make sure you get an answer. I know there were a lot of them that came at the very end there that I'm not entirely able to get to, but the other option with that is you can find GIA on Instagram, Facebook, LinkedIn, and Twitter. And I assure you that when these questions come in, they find a way to get them over to us to get you the answers. So I'd like to thank you all for coming, and we hope you'll join us again for the next GIA Knowledge Session. And I'd like to thank Dr. Yun Lua once again for this excellent presentation and the nice insights into fluorescence and diamond appearance. Thank you, Yun.
Thank you, Mac. Thank you, everyone.
All right. Goodbye, everyone.
Bye.